Hi, welcome to the next in our series of video lectures on practical electromagnetics for engineers. Now that we understand that magnetic fields and magnetic forces really are just electric fields and electric forces in the case of moving charges, and that magnetic fields are created by current elements that replace charges, which created the electric field, we're ready to look at some of the relationships between fields. And today we're going to study something called Ampere's Circuital Law, which is actually easier to understand than it is to pronounce. If you're in my class, you can follow along in section 5-3 of the textbook. So if you remember back when we were studying electrostatics or electricity that didn't move around in time, we saw there were relationships between the thing that generated the field, which was the charge, the field itself, or the flux, depending on how you measured it, and also the potential energy that was created by the field, or the voltage. And since we see magnetic fields are intimately related to electric fields, we might expect that there be the same types of mathematical relationships that would allow us to convert magnetic fields and current elements and things like that together. So the point of this lecture and the ones that follow it are to establish these relationships. Now, because we've learned about all of this in electric fields, it doesn't really, what's a good way of putting this? It doesn't really seem worthwhile to go into it in the same amount of depth. So we're going to go through this much more quickly and establish the relationships and offer them in a way without proof. It turns out that they can be very hard to prove and very hard to understand, but the relationships themselves, if you understand electrostatics, understanding magnetic fields is actually not that difficult and not that different from it. So where are we to date? We know that we have current elements that create magnetic fields. They're essentially the generating term, and a current element, remember, is a tiny little piece of current pointing in a particular direction, dl, of some magnitude we're going to call I naught. And these current elements, through the Biot-Savart law, essentially create magnetic field or magnetic flux, and these are related by a quantity mu we call the permeability that we're going to get into later. And we know it's actually somewhat difficult to calculate the magnetic field from the current element because you've got this integral right here that contains a cross product as well as a cubic term in the denominator. And remember, whenever we see a cross product like this where we have the difference between two vectors, in the full case, unless you can ignore some stuff, this turns out that there are 12 integrals involved that you have to solve. So let's look at filling this out and looking at maybe a relationship that doesn't go from current to flux, but from the flux or field back to the current. And remember, in the electronic case, or the electrostatic case, we had Gauss's law, which said that the divergence of the electric flux was equal to the charge enclosed. Is there something similar in magnetics? So the question we want to answer is, there a Gauss's law for magnetic fields? And since we don't know the answer to that yet, let's put a question mark there because we don't know. We remember that in the case of the electric field, the divergence, del dot D, which happens to be a scalar quantity, was equal to the charge enclosed. And the way we thought about this was, if you had flux vectors that were going into a volume, or there were more arrows going into a volume than were coming out, you saw that this essentially was what we called a sink, and the divergence was negative. In the case you didn't have any vectors that ended inside the box, they didn't begin there and they didn't end there, we saw the divergence was 0. And in the case where you had more arrows going out of a volume than you did coming in, this happened to be a source of a vector field, and we saw that the divergence of this space, or the value of the divergence at this point in space, was positive. And remember that what we found in the case of the electric field was we could put boxes pretty much anywhere, and we found the divergence was 0, except if we put a box around where the charge originated, in which case we saw all the arrows are going out, and that's equal essentially to the charge within the box. And that's Gauss's law. That's essentially this equation right here. What happens if we do this in the case for a magnetic field? So we have a box there, we have a box there, we have a box there, and let's put a box around the origin there as well. It turns out, because of the swirliness of the field, that obviously in these cases out here, no arrows are starting there or ending there, so the divergence is going to be 0. But even near the current element, and remember the current element, which is that little black dot right there, is coming out of the screen at you, because the right-hand rule says it comes out if it's going to basically create an electric field that rotates around counterclockwise. Even here, you can see that the arrows are going around in a circle, and an equal number of arrows goes in as comes out, and so the divergence is equal to. What this means is that the divergence of the magnetic flux vector B, and hence H by comparison, is equal to 0. And what this means in real terms is there's no such thing as a magnetic charge. You don't have something like a charge that pushes stuff out in magnetic fields. At no place do you have accumulation, i.e. sinking of fields or squirting out or sourcing of vector fields in magnetic fields. The divergence in every case is equal to 0. There are not magnetic monopoles. So we can go ahead and start to build our magnetics triangle by putting one equation right down there, which is the divergence of the magnetic flux is equal to 0, which says there's no magnetic charge. But this doesn't really help us convert from magnetic field or flux back into a current element, the way we want this arrow to go, like that. So how do we do this? Let's revisit one of our other laws that we had in electrostatics, and now we're going to get into what we're talking about today, which is called Ampere's Circuital law. Remember that for an electric charge, so we have essentially some charge Q here in the middle that's giving rise to all those electric flux rays that are going out. No matter how we did a closed integral, a closed line integral, so some path through this space, we found that the electric field along the direction of the line. So here's our vector dl, remember, and our electric field is those blue arrows. If we sum this up piece by piece by piece by piece by piece around this integral, or around this closed line, we saw that was equal to 0. And we saw this is just conservation of energy, because you don't want to be able to have a charge do a closed loop and get more energy each time, because then essentially you'd have a perpetual motion machine, and we know that doesn't happen. This is obviously not the case in a magnetic field, because while you can do a circle here, and you can make the case that as you add the magnetic field, which is the green arrows with each little element, dl of this, out here, that you're going to get 0. Obviously, if you put your ring like that, then you will get an addition as you go around. Every single one of these arrows contributes coherently, or is going to sum up to something that's non-zero because of the swirliness of this field, because it rotates around like a whirlpool or a tornado. And it turns out that when you express this and you calculate it all out, you come up with this, which is Ampere's Circuital law, which says if you take a contour and do a contour integral, remember this little circle on the integral sign says we're doing a contour integral. We're going around some closed path that starts at one point, and even though this doesn't show it very well, is going to end at the same point. When we do that, the total value of summing up all the magnetic field along the direction of that line, piece by piece by piece by piece, is equal to the current enclosed, which in this case is our little current element I. So again, Ampere's Circuital law says that if you go around a closed line and basically sum up the magnetic field dotted with the direction the line is going, that little element dl, that the value you get is going to be equal to the current that's enclosed by that line you just drew. Now this is getting to be more like it, because now we actually have an expression where we can go from a magnetic field and end up with a current. So we actually are going from here back here. The only thing I don't like about this is that we have an integral going this way, and we also unfortunately have an integral going back that way, because we have to do this integral around a closed loop. We'd like to have a differential equation if we can, and this also doesn't really tell us what's happening at any point in space. It essentially tells us what's happening around a loop, but not at a single point in space. So we're going to go into something called the curl of a vector field now that's going to help us resolve this. If you understand curl and know vector calculus, you can skip ahead a little bit in the video. So the question we're trying to answer is, how do we get a point measure, understand essentially the circulation, the swirliness of a vector field at any point in space? And we're going to make an analogy of a little paddle wheel here. So how does that work? Essentially what I've got here is I've got a vector field. That's the black arrows you see all over here. And this is something I generated mathematically using MATLAB to display. And I want to know, at any point in space, does this vector field have some swirliness? Does it essentially move around in a loop or not? And one way I can think about testing this is to think about making very, very little tiny paddle wheels. And you can see that I've drawn 3 paddle wheels. Paddle wheel number 1 right here, paddle wheel number 2 right here, and paddle wheel number 3 right there. it's pretty clear to me that paddle wheel 1 is in an area where things are just flowing in one direction. And so while this side of the paddle wheel is going to feel a force that way, this side of the paddle wheel is probably going to feel an equal force in that direction, and the paddle wheel is not going to spin. There's not going to be any force in either this way or this way because the arrows aren't going that way. If we take a look at paddle wheel number 2, this seems to be in an area where you probably have larger vectors or stronger forces going that way and weaker vectors going that way. So there's a chance that paddle wheel number 2 might actually spin, and if it does, I would kind of expect it to spin around in that direction. Paddle wheel number 3 is not so clear, and that's why I chose it. You've got essentially longer vectors on this side and shorter vectors on that side, so maybe it's going to feel a force and spin in that direction as well. How do we determine this? And essentially what we're doing is we're using these paddle wheels as a way to get a point measure of circulation of any vector wheel. We put in this imaginary paddle wheel, we see if it spins. If it spins, then the vector field has some kind of swirliness or circulation to it. And the way I can think about whether a vector field has circulation is to simply sum up the forces around the circumference of the paddle wheel. So essentially if we do the integral and essentially go around this paddle wheel, summing up the forces at a very tiny point in space, this integral, if it is basically 0, it's going to say there's no circulation. If it's positive, then you're going to get a counterclockwise circulation because of the right-hand rule. And if it's negative, you're going to get a vector pointing into the screen, also because of the right-hand rule. But at least this will tell us whether there's a swirliness or not. The problem is we'd have to do an integral at every single point in space, which is really annoying. Well, it turns out there's a differential operator called the curl that tells us this information without having to do an integral. Remember, if we could figure out this integral, we'd know if any point in space had a circulation to it because we're just summing the forces around the circumference of a paddle wheel. Another way to think about this is to say, if my paddle wheel is square, for example, if there's a force that way and a bigger force that way, my paddle wheel is going to go that way. Also, if I think of the tops and bottoms of my paddle wheel, if there's a force that way at the top, or the bottom, excuse me, and that way at the top, then I might get the paddle wheel to go that way. How do I measure this? Well, if I just look at the difference between the top and the bottom, which is the change in y, and I look at the difference between the left side and the right side, which is the change in x, I might be able to understand which way the paddle wheel is spinning. And of course I have to think of taking the difference of these things because, as we saw, whichever one's bigger is going to basically determine which direction it goes, because the way I've drawn this, it's not clear. If we want to write that out mathematically for a vector field in x and y, we have this expression right here. We ask, what's the change of x of the y components? So these are the y components here and here. How does that change in the x direction? That's this expression right here. We can similarly ask, how do the x components, which are this one and this one, change in the y direction, which is that way, which is this expression right here. So if I calculate this term using derivatives, I might be able to get an idea of which way the paddle wheel is spinning. And so what I've done in the 3 cases of paddle wheel 1, paddle wheel 2, and paddle wheel 3, I've gone ahead and expanded that out. And essentially, if you look at case number 1, what I've done is I've represented the vector field as the blue arrows right here, and I've represented the x components as gray arrows and the y components there also as gray arrows. And now I can ask, as I go essentially in the x direction, are the y components changing as I move in x? Well, here's a y component, here's a y component, here's a y component. That's not changing as we move in x. They're all the same length. I can also ask if the x component of the vector is changing as we move in y. Well, here's an x component, here's an x component, here's an x component, and they're not changing. So in this vector field, I can say the rate of change of the y component in x is 0. The rate of change of the x component with y is also 0, and so I would expect that this paddle wheel number 1 to have 0 circulation. And in fact, that's true. And so essentially you can say, I can essentially get this integral by summing up the change. Let's look at another case. Here are our x components and our y components. So if we go across the middle line, we can see the change of the y components as we go in x is in fact going to be positive because these y arrows are getting bigger as I move in the x direction. If I look at the change of the x components as I go in the y direction, i.e. look at the horizontal arrows as I go that way, we see that those changes are negatives. The arrows are getting smaller as I go up. And so now what we see is that we have a positive component minus a negative component, which gives us a net positive component. And so this calculation essentially says there is swirlishness to this vector field. The swirlishness is positive, which by the right-hand rule means we're going to go that way, counterclockwise. So if we take a look at this, we see that paddle wheel number 2 here should spin in that direction. And if you think about it, superimposing this paddle wheel on top of that vector field, that kind of makes sense to me. Let's go ahead and look at case number 3. We'll leave this as an exercise to the viewer, but it's pretty obvious to me if you look at the x components and how the x components are changing in y. Those x components are 0 because these arrows are pointing straight up and they don't have any x components. If you look at the y components as they change in x, as we move this way, those y components are getting bigger. So we would expect this also to have a positive value, and we calculate this expression right here. And thus we would expect paddle wheel number 3, if placed in the middle of that vector field, to rotate via the right-hand rule in the counterclockwise direction. And so the vector is going to be in the z direction because the axis of this paddle wheel sticks right out of the screen at you, and you can see that in fact there's where the z is right there. Now, without going into a lot of unnecessary detail, we can represent this by our del operator. And remember, our del operator is shown right here. It's the change in x in the x direction, the change in y in the y direction, the change in z in the z direction. And we take the cross product, which we learned in the last video, of any vector field. Del cross any vector field gives us something called the curl. It's given by this expression right here. I know it's complicated, deal with it. And it essentially, if we calculate this, is going to tell us the swirliness of any vector field. And the example you just saw, the vectors were only in the x and y direction. So that term is 0, that term is 0, that term is 0, and that term is 0, and all we calculated was this. In the more complicated three-dimensional case, you don't just have 2 elements, you actually have to consider all the elements in this expression. So, to quickly summarize, we have a point measure of the circulation of a vector field we call the curl. It essentially tells us the forces around the outside of a paddle wheel. Given the del operator right here, we can define the curl to be this expression right here, and that value is essentially going to tell us whether this paddle wheel is going to rotate that way, which we consider positive by the right-hand rule, this way, which is negative. In other words, this vector arrow that you see there is going to point down rather than up, or if the value of the curl is 0, that paddle wheel is not going to spin at all. Woof, that's a lot to go through, but unfortunately we're not done yet, because we can simplify things immeasurably using something called Stokes Law. And I'm not going to go through the full mathematical derivation, but let's do a simple derivation of Stokes Law. What we saw is that we have a paddle wheel, and let's consider a square paddle wheel because it's easier to deal with, that the overall circulation could be measured by essentially either the sum around the circumference of all the forces, or by the curl, del cross the vector field we stick this paddle wheel in. And we can basically, in this, simply sum up the y direction plus the negative x direction plus the negative y direction plus the positive x direction to calculate this integral and calculate the forces around the circumference. It turns out that overall, if we calculate the forces around the circumference, we can essentially ignore these two sides because the integral is going to cancel out there. Anything we add in that direction is going to be equally canceled in that direction. So we essentially ignore that, and we know this integral is equal to essentially the curl of this square number 1 or paddle wheel number 1 plus that paddle wheel number 2. So here's term number 1 and here's term number 2. Let's extend this even further. You can see that if we have 4 paddle wheels, the sum around the outside of a larger square is only going to be due to these components, because that component, that component, that component, and that component aren't going to contribute to our integral because they're going to cancel. And so a more general expression is that if you take an integral, a line integral, around a closed loop, that's this expression right here, that's equal to the curl integrated over the surface. So we basically calculate the circulation at this point, this point, this point, this point, and if we sum up all of them over that surface, that's what this expression is here, and we should know that this is a surface integral by now. These things are equal to each other. So essentially what we've got is a way to two ways to determine the swirlishness of an area. We can either take the integral around their circumference, or we can sum up all of the circulation over a surface, and they're exactly the same thing. And this, in a nutshell, is Stokes' law. Now we start to get into some mathematics here. It turns out that we know by Ampere's circuital law that the total current enclosed in any circulation is equal to I. In other words, if we draw an area, a line around an area, if the integral around that circumference is a positive number, we have a positive current, and we can set that equal by Stokes' law to the sum of the curl over that area. This is just a mathematical equality, nothing new intellectually here. But we also know from when we studied conductivity that the overall current through any area is just the surface integral of the current density J through that area. And go back and watch the conductivity video if you don't understand this, but we just sum up all the current density J over an area and we get the total current through that area. So we can set this equals to Stokes' law, and then we observe something. These are both two surface integrals, and that means that the overall current density J is equal to the curl of the magnetic field. And this actually is a really important result, even though we got it through some mathematical manipulation in a roundabout way. We're going to use this a lot later on. So essentially this leaves us in better shape with our magnetics triangle. We can go from current elements back to fields and fluxes via the Biot-Savart law, which unfortunately involves a complicated integral that's going to have 12 components in the most general case. And we have two ways to go from the field or flux back into currents. We can either do Ampere's circuital law and sum up around the circumference the magnetic field, which tells us the total field enclosed, or if we have a more distributed type of field or current, we know that the current density is just the curl of the magnetic field. And so now we're starting to flesh things out and understand these relationships. But what we haven't yet determined is whether there's some kind of magnetic potential, like we had an electric potential we called voltage. And that's the subject of the next video lecture. Let's just review really quickly. If we compare an electric field, E, which is here in the blue, and a magnetic field, H, which is represented by the green vector field over here, we see that we have Gauss's law, which says that for an electric field, the divergence of any area is equal to the charge enclosed. So all of this region out here is going to have zero divergence, but if we put a box around here, there's a charge there, so we get a positive value. We know that if we do a surface integral and sum all the little components around the circumference of this line, that in an electric field this term is equal to zero. That's just conservation of energy. And then by Stokes' law we can make the jump, which we haven't made before, that the curl of an electric field is equal to zero, at least in the static case. There's no curl to an electric field if the electric field isn't changing. For the magnetic field, we've learned that the divergence of the magnetic field or magnetic flux B is always equal to zero, because there's nothing like a charge that gives rise to arrows coming out. Everything always goes in loops. So if something starts somewhere, it's going to end somewhere. You can never draw a box here that has more arrows going out than going in. They're always equal. There are no magnetic charges. We've also, through Stokes' law, learned that if we want to sum up the total current, we can either take a line and sum up all the components, or treat this line as a paddle wheel and take the curl at any point in space, and over some area we can sum up all the curls, and this in either case gives us the charge enclosed. And from this and from Stokes' law we have a more general representation of a distributed current density J as being the curl of the magnetic field H. And so these are a lot of mathematical relations, but we're beginning to relate one to the other. And because we've gone into this previously in a fair amount of depth in the electric field, it shouldn't be too hard to think of the same types of mathematical equations as representing a magnetic field. Sure, they're different, but doing the math is pretty much the same.